Okay, hello. My name is Emmanuel Emiliano. Uh, for my name, 131 18 211. So now I'm going to explain about the creep phenomena for resisting alloys. We'll start with the definition. The definition is the materials are often placed in a surface at elevated temperatures and exposed to static mechanical stresses. The formation under such circumstances is termed creep. The time-dependent and permanent deformations of material when subjected to a constant load or stress. It is observed in all materials types for metals. So, for the generalized creep behavior, a typical creep test consists of subjecting a specimen to a constant load or stress while maintaining the temperature constant. Deformation or strain is measured and plotted as a function of elapsed time. Knowledge of these creep characteristics of a material allows the designer engineer to ascertain its I mean suitability for a specific application. For the typical creep curve, it is divided into three regions, which are primary region, secondary region, and tertiary region. Primary region occurs first, typified by a continuously decreasing creep rate. This suggests that the material is experiencing an increase in creep resistance or strain hardening. For the secondary region, sometimes termed as the steady state creep, the rate is constant, that is, the plot becomes linear. This is often the stage of creep that is of the longest duration. The constancy of creep rate is explained on the basis of a balance between the competing processes of strain, hardening, and recovery. For the last region, it is the tertiary region. There is an acceleration of the rate and ultimate failure. This failure is frequently termed rupture and results from microstructural or metallurgical changes. For example, grain boundary separation, and also the formation of internal cracks, cavities, and voids. And this is the typical curve that I've told you about. As we can see here, this is the primary region, and then this is the secondary, and then this is the tertiary. Here where I explain the steady state creep rate, which is the secondary region. It is the engineering design parameter that is considered for a long-time application, such as nuclear power plant component that is scheduled to operate for several decades. Here. Now I'm gonna explain about the effects of stress temperature on creep characteristics. These are the graph. As you can see, this is the first graph, this is second graph. The instantaneous strain at the time of stress application increases, the steady state creep rate increases, the rupture lifetime decreases, and T should be greater than 0.4 Tm. The empirical relationships have been developed in which the steady state creep rate as a function of stress and temperature is expressed. Its dependence on stress can be written as this formula, which N indicates the material constant, and for the K1 is the material constant also. As we see before, at the second graph, it is a plot of the logarithm of P versus the logarithm of S yields as a straight line with slope of N. This shown in figure 832, which is the second graph that I showed you, for an S590 alloy at 4 temperatures. Clearly, one or two straight line segments are drawn at each temperature. Now, when the influence of temperature included, we get this formula, which K2 indicates the material constant, and for the QC, the activation energy for creep. There are types of creep mechanisms, base mechanisms, which are dislocation, non-dislocation based, and diffusion based. For the dislocation based, there are cross slip and climb. Non-dislocation based, there are diffusion and grain boundary. And for the diffusion based, Nabarro hearing and cobble creep and power law. Now I'm gonna explain some of the examples. The first one is Nabarro herring creep. In high temperature, the diffusivity will be higher and will result in easier atomic jump. Diffusion happen at the crystal lattice region. The diffusion will cause grain boundaries parallel with the stress to become empty as the atoms move toward the grain boundaries perpendicular to the stress direction. And then cobble creep. The characteristics of cobble creep, it mainly occurs by grain boundaries. It happens at lower strength and lower temperature. The strain rate of a material experiencing cobble creep is given by this formula. Then power law. Power law, moderate stresses about the 0.6 tm. It is widely believed to be dislocation climb control, have relatively higher stresses, and the creep strain rate is determined by the rate at which the dislocations are able to climb over obstacles. These obstacles may be the long-range stress fields surrounding dislocations or incoherent particles within the lattice. The strain rate of the mechanism is given by this. And the next one is the Larson-Miller parameter. As we can see in this graph, it is a graph plotted from stress versus the Larson-Miller parameter of this model based on Arrhenius rate equation can be defined as this. M here indicates the LMP, which is equal to T times C plus log TR, which this T indicates temperature, TR time before failure, and C is the material specific constant. This parameter will allow for engineers to calculate the result of a creep test with a shorter time. And then heat resisting alloy microstructures. Heat resisting alloy microstructures has a very high melting point for a material, will make it more prone to creep. The bigger the grain size, the better a material is resistant from a creep. Comparative with grain size, little grains license more grain boundary sliding. These are the examples, which are large grains, equiaxial, directional, and single crystal. That's all for the summary from me, and thank you for listening.